Hi, my name is Jonathan Craig, and this is my final individual presentation. My major achievements for sprints 3 and 4 are I implemented a deterministic finite state automaton to process text to recognize speech into key presses. I implemented processing of voice commands to change desktop controller modes between command, macro, key press entry, and streaming modes. And I implemented processing of voice commands to perform essential desktop controls such as window navigation, text entry field navigation, select copy paste, and a function to undo text. As a user, I want to enter and leave a key press entry mode so that I can differentiate between whether or not I am dictating commands or individual key presses. All of the modes in our project are organized in a state pattern another teammate implemented. For switching the modes with voice commands, I created a threaded runnable state machine that processes voice commands to get the state the program should be in, or to access other meta functions in the controller. I do this by tokenizing the incoming stream of commands into a buffer. From there, I examine the tokens sequentially. Should the token match our meta switching keyword, the next token is checked to match against a mode or meta command keyword. If it matches, the mode state is switched accordingly. Once in the appropriate mode, the outgoing message buffer is given to the appropriate mode state's execute function for handling. In key press entry and streaming modes, I have implemented a deterministic finite state automata to process spoken word into key presses. Here's a class diagram related to the classes for the key press mode. As you can see, I have a state machine, which has an incoming buffer and a confirmed buffer. We queue the string, tokenize it, and analyze it, and then once it's good, it is flushed into the confirmed buffer and sent out. The machine here is the actual DFA machine for the finite state automata. So that's the actual DFA, which has its own schema. And here we have the hypervisor, which observes the state of the machine and gets the processed information out of it. And over here we have a keyboard robot for entering commands and performing the actions on the user's keyboard. And here's a sequence diagram for a user voice to key press use case. So as you see, on an incoming command from the dispatcher module, we queue that string if it's intended for us. State machine determines what state we're in, and then gives it to the appropriate execute function, where you get the string command and the configuration data. This is pushed into the DFA machine, where it tokenizes it and pushes these tokens until it hits a terminal state. And that state's information is sent over to the hypervisor, where it checks it out, observes it, and parses it, and creates new key presses for the keyboard robot to press. As a user, I want to select a text input area in an application so that I can enter text in an application. To accomplish this, I use the same mode switching keyword followed by a keyword that indicates the user wishes to switch text boxes. The keyboard robot is then called to execute the appropriate key presses. As a user, I want to navigate through my open application so that I can switch focus. To complete this story, I similarly use my existing infrastructure in the state machine to detect the mode switch and the appropriate trigger word. A keyboard robot is called using a sequence of trigger words: alteration Alt to direct the robot to hold down the Alt key, alteration Tab to hit the Tab key, and you can do that as many times as you wish to iterate through your tabs, and then the Alt command again a final time to confirm the tab you wish to select. As a user, I want to direct the window manager to minimize an application with my voice so I don't have to minimize an application with mouse or keyboard. I again use the same mode switching logic to direct the keyboard robot to minimize or maximize the currently targeted window. As a user, I want to be able to select, copy, and paste using voice commands so that I can more easily edit text. These functions again use the word switching keyboard, but there's a little variation in this. So we select by selecting at the current cursor cursor location by saying the alteration select directive. The user then says move X number of spaces left, right, or wherever you want to move to select the appropriate text. This moving functionality is accomplished with help of that deterministic finite state automata. So this directive, move X number of spaces left or right, is tokenized and parsed by the DFA, and from there we can get the appropriate action, which is move, the number, which is X, and the direction, which is left or right. After we have that information, we call a keyboard robot to execute based off of that. The copy and paste are done similarly. As a user, I want to have a directive in keypaste entry mode that indicates I intend to cancel a word or key that was spoken so that I can more easily write and edit text. To implement this, I created a threaded logic in the DFA hypervisor class to maintain a linked list of integers that corresponds to the number of characters associated with the key press directives that have been spoken. As a token is processed, its context is returned, meaning if a map directive such as alpha corresponds to a key press A, one character, the key press A, will be removed on the undo. Should it not map back, it is a token that's intended to be typed as is, like my, or name, or is. The size of this token is added to the linked list. So in the case of my, 2, name, 4, is 2 again. And that number will be removed on the undo. The linked list is updated as tokens are added and removed. The user treats the undo as a map directive in the schema, but instead of corresponding to a key press, it corresponds to the removal of the last token typed. Here's the schema grammar for the automata that I've been referencing. So as you see in this, there are kind of 3 action branches: type, move, and backspace. In the type state, you get to here and you can type any number of letters or tokens. In the move state, you can move a certain number of spaces, and you can either move a direction, whether that's up, left, down, or right. And in the backspace, there's only a number of times to backspace. And as you can see, these all have ways to cancel these if you wish to restart. And like I said, you can, on the type branch, say you're entering a token alpha, bravo, my name is. You can also say undo, and it'll have the effect of pulling the last one you entered off of this stack you're creating. In conclusion, I've implemented a complex real-time natural language parsing system as well as essential quality of life desktop controls based on the parsing of spoken word. The system is capable of handling other schemas as grammars aside from this one, making it greatly extensible. And I believe that's my presentation. Thank you for watching.